Okay, welcome to the DTC seminar. Today we are very happy to have Dr. Jiang Zhu, or like Zhu Jiang, from University of Alaska. He graduated from University of Alaska and, of course, major in atmospheric sciences. And I guess he hasn't left Alaska because he's working at Geographic Information Network of Alaska in Physics Institute, still University of Alaska. So his major research interest is application of satellite data in atmospheric sciences. And he is now a DTC visitor, and today he's going to report on his DTC visitor project, satellite wind data assimilation in HRRRAK-like model. So, welcome.
Yeah. Hello, everyone. Thank you to come to my presentation. Yeah, this talk is about the satellite wind data assimilation in HRRRAK model. So I want to talk about briefly introduce the project and then talk about design the experiment and the data set, and how to pre-process the data in order to get into the data assimilation. And I have a case study, and I have a 1 month forecasters used to static analyze, and finally give the conclusion. HRRRAK is a high-resolution rapid refresh for Alaska. This model is right now in NOAA is operational. But in this model, we satellite wind data are not assimilated in this model. But as you know, in Alaska, we benefit from many polar orbiter pass every day. Actually, my work unit received the polar orbit data and produce this satellite product and deliver to the National Weather Service and other users in near real time. So this project is we want to know if the wind data from this derived from satellite can be used to assimilate into our HRRRAK model, so that it can see if we can improve this model run. So in order to do this, answer these questions, we do the design the experiment. So we have we build a HRRRAK-like model, which is the similar configuration, which have the same domain, same resolution, and parameters. And the initial field is from the RAP. It's just like the HRRRAK Alaska model, which is run operational route. So we build this experiment model on AWS cloud system, as well as on our local machine in University of Alaska. So we designed the experiment to run this model in three models. One is the control run. For the control run, we don't do any data assimilation. Another is the experiment run 1. This one, we assimilated wind data plus conventional data. Experiment 2, we only assimilated wind data. So we use the GS 3D bar analysis in this data assimilation experiment. The data set for the case study, we got the data from personnel from DTC. Thank you, DTC person. For the statistic study of the monthly forecast, we download the data from the NCDC. And for the wind data, we only, in this experiments, we only use the virus wind data. We could use other wind data from other satellite. This project, we only use this kind. We downloaded this wind data from the class, the W class NCDC. So the basic things we need to get into the wind data into our data assimilation. We treat the various wind data as the ADPUPA record in the GDAS profile file. So we read the various wind data and pick the good data. So the good data here we defined is the quality is greater than 80%. So in the various wind data they have the quality flag. So the flag, the value of the flag is from 0 to 100%. In order to keep the good data, only assuming the good data, we use this quality, this condition. So this is a little more detail for how do we do the pre-process of various data into the convert it into the pre-buffer file. This shows the logic of this. So after we get this various data from the let CDF, it converts into the pre-buffer, and only choose the data which have have a quality flag greater than 80%. After we get this, we can start to do our case study. So in the case study, we run the HRRRAK-like model to do the 24-hour forecast for 2018 June 6th and zero time UTC. And here I show you the domain definition and the good data in the domain. So this is various data only. This is we got it because the various data is each granule. So we got several. We have a criteria. We choose the time window is 6 hours, 3 hours before and 3 hours after your analysis time. So we got the data. This is the whole data in here, but this figure doesn't necessarily reflect how many points, how many data actually in this in this domain. So here we're talking about here is a three level like 300 millibar, 500 millibar, 8500 millibar data in this on this level. So there's a whole data, but after we apply the quality control for this data, we only choose the greater than 80%. The quality is greater than 80%. Only choose that data. We got the data looks like this. So it's very, very causal. Yeah. But this is for this case. So maybe for other cases there are a lot of cloud. They can they can derive another wind. So, but for this specific case, is very causal here. So after we get this, for our 3D bar analysis, we pay attention these two conditions, try to control to make sure it actually assimilate our data. So it's in the GSI name list we have this one set up. Because as I told you before, we convert our CDF into the pre-buffer. So here is the pre-buffer data. So it's from one, which means it's tech. Another control, quality control. Okay, thank you. Another control is in the info file. So here we convert the various data, treat them as a 220 type in the pre-buffer, so to make sure it get into. So here's the analyze the incrimination of the increment of the two experiments run. For on your left is experiment 1, which assimilated various wind data plus observation data, and on your right is various data only. So as you can see, because they're on your left, because we have a various combined with the observation data, there's a lot of data. So you can find that the increment is a lot. There are a lot of increment here, the change. But for the various only data, because the data is very causal, so you can say the change jumps. There's just some place.
Can you point out like which figure, like which variable? Let's see that.
Say again.
Like the which variable, like the which plot is for like which variable?
Oh, okay.
UVTQ.
Yeah, UVTQ. Yeah, there's a T, there's a U right here. There's a V. Oh. There's a relative humidity. Oh. Yeah. Sorry. sorry. It's just. So this is give you the detail of the increment assimilated by our wind data only. So you can see the data here. We have the data here. They'll give just like the change. So that means our data is assimilated into our assimilated and modify the initial condition. So from this case study, we know if we only choose the good variance, which is greater than 80%, so that the wind data is causal, it's very causal. If we only assimilate good data, that will have very little impact on our initial field. Yeah, only this spot has some change. The impact is a little.
So you have data points in the Gulf of Alaska?
Yeah.
I don't see any impact in that area. Does that?
Yeah, like I said, because we only right now do the various data, and the various data is very causal. This is I show you the data here. The only find it here, but you find this impact this here, but this one, yeah, you couldn't find this one. This is this. I think this just tell you. There's two things I'm thinking. So after you get this quality data into your data GS file, if this in the GS file they still have itself quality control of the data. So if that data doesn't meet the control, they will not accept assimilate into the data. This probably is this reason, but I'm not sure. I'm not quite sure. But you can find David, these 2 points is here, have an impact here.
Yeah. We can check a lot of things to see why that's 3.
Yeah.
Yeah, we have a way to check why that 3 data are not there. And also another possibility is these 3 data agree with background 100%. So they don't need an innovation. There are lots of possibilities, but we certainly can see, but at least you got some data there.
Yeah.
Okay.
Thank you. So this is for just show you the data is too causal if we use the quality control 80%, and if we use only this good data, try to impact the initial condition, that impact is very subtle. Okay, but as I said before, that is the only case we show. It show you the good data is very causal there. You never know if the other day they have a more cloud, they probably have more good data. So we do the 1 month forecast and then do the statics analysis. In this one, we run a customer's Alaska HRRRAK model, which is we use the smaller domain and the lower spatial resolution. And we run the data 4 times a day and do the 24 hours forecast. And we use the MET tool to pair the forecast with the observation. And we calculate the RMSE of the 3 variables, the temperature, RH, and the wind speed, and 3 pressure level. So this is the result of the RA. Here to show you is the ratio of RMSE of the 2 different experiments. So on your left is the RMSE ratio of the experiment 1. The right one is the experiment 2. So as you can see here, the RMSE ratio. By the way, RMSE ratio is defined by the RMSE of experiment 1 divided by the control arm. And the right side, the ratio is the RMSE ratio of experiment 2 divided by the control arm. So if the ratio less than 1, if it's more or less, that means more good. Yeah. So the ratio of the 3 variables and the 300 millibar pressure is fine. So as you can see left, if you use the data simulated the VIRS plus the GDAS observation data, you get your ratio is like this one. Yeah, your ratio is the first one is the temperature. This is humidity. This one is wind. So in both, in all the temperature, humidity and wind, and in 3. This is a 300 level. Let me show you there. This is a 500 level. And this is 850 millibar level. So three variables in three pressure levels. They show the ratio is less than 1. This is for the experiment round 1. That means this data assimilation in the experiment 1, which assimilated both GDAS data and the various data, that improve your initial condition. But for in your right hand, this will show the RMS-E ratio of experiment 2. That is, we only assimilated the various wind data. So, as you can see on your right hand side, in a 3 pressure level, 300, 500, 800, and the 3 variables, they're very close to 1. So that means for the analysis of the 1 month forecaster, if we only use the various data to assimilate it, the conclusion is very close, almost no impact on the HRRRAK forecaster. So this is table tell you in the table they give you the ratio of this. So you can see in the experiment 1. This is a analyzed time. This is a 6-hour forecast, 12 hours, 24-hour forecast here. So for the experiment 1, the data assimilation improve our initial condition a lot, like improved 25% probably. This is around the 0.75. But this improvement will decrease. It's very limited. So if we check the 6 hours forecaster, 12 hours forecast, and 24 hours, it's almost close to 1. It's 95% or more than 95%. So it means your initial you change your initial condition, but this initial condition not carry on into your forecast for a long time. It's just very short time. Probably 6 hours you still get some, but after 12 hours to 24 hours, that impact is disappear. So for the experiment 2 run, so we as I can say that before, we don't see any improvement in the analyzed time. So in the 6 hours, 12 hours, and 40 hours, so there is almost close to 1. Yeah. Yeah, this is I just give you the reading from the table. I get this conclusion. So finally, we get the conclusion from this study. Even if Alaska gets intensive polar orbiting satellite coverage, various data with good quality is too coastal in Alaska. So assimilation of this coastal data in a model initial field does not improve the model forecast. I mean, here we only think about use the good quality. If we open wider, get the lower quality into the data, maybe they have some different. But in this experiment, we'll only use this good quality data. The second is the conventional observation data has much stronger positive impact on model initial field than various wind data only. Even if the impact is time limited, it does impact short-term forecast results. So because our HRRRAK model is focused on the short-term forecast, so So for this kind of application, you use your observation data assimilation is definitely benefit. The combined satellite wind data and the conventional observation data can be used to assimilation in the initial field. This is the conclusion. So this project is supported by DTC visiting program. So thank the DTC. Thank you very much. Special thanks goes to director Louisa Minghu, travel and Chunhua, and also Jessica. She doing another logistic things for me. Thank you very much. Do you have any questions?
Yeah, questions. Any questions? Okay, Louisa.
Amazing, I'm not a data assimilation person, but is this on?
Yeah.
Okay. This is a really basic question with respect to, so you initialized with the RAP fields, is that correct?
Yeah.
And then, or that was your background for your data assimilation increments, correct?
Yeah.
But then, so when you, so it's twofold. So when you assimilate the conventional data, that data has already been used in the RAP analysis? Is that correct? Okay.
Yeah, I think so.
Okay, so, and granted, it's a different resolution domain. But I guess the key part of my question is, then what observations are you verifying against? Are they independent of what was done with respect to the conventional data, or are you basically just looking to see how closely your analysis, when you include the conventional data, matches your conventional data? Did I make any sense there?
Yeah, I know what you're asking. I use when we do the comparison, I use the observation data as a base and ground truth. Everything compare against the ground truth data. The ground truth data itself get from the GDAS Pro buffer. I travel that out. Yeah, use the MET tool to do that, the pair comparison. So as you can see here, for this analyze monthly, everything we calculated the RMSE. Everything is first use the MET to get the pairs. The pairs is observation data with your forecast output. Get the pair and get the whole month's forecast data. It's about the 670 pairs and calculate the RMSE. So to answer your questions, we use the observation data as a ground truth base. Everything compare with it.
Right. So I guess actually my question is, how much, if any, of the observations that you used for your verification are independent of what was put in your analysis of experiment 1? Are they identical, or is there some data that's in the...
It's identical.
It's identical.
Yeah, because I trapped the ground truth data from the GDAS profile. And I also use the GDAS profile, combine the wind data together to assimilate. Yeah.
Okay.
So is it possible to assimilate U and the V component separately? Because instead of the UV, I thought it's the magnitude of the wind instead of the wind component, wind vectors. If you simulate vectors, that way improve the circulation. I think that impact will carry on probably a little bit longer.
Oh, okay.
Is that possible to simulate?
I checked our GDAS. I think it's possible.
But you just simulate.
I'm not quite sure. I think Minghu can answer.
In GSR, you can, okay. In GSI, you can assimilate U and V together. That's basically vector, right?
Yeah.
Or you can assimilate speed only. Speed, not the direction, speed.
But you cannot assimilate U and V separate.
Okay, U and V, you have to assimilate them together. Basically, that means you have U, you do have V. You cannot only assimilate U, but you can assimilate speed only. Basically, speed without direction. That's basically.
Direction would be very important.
Lots of wind has no direction, right? We have a speed, but we don't have direction. Some wind. Okay.
So I think because we assimilate U and V, so it's a vector.
Basically, it's vector
like
actually.
The same thing and the same thing you're talking about. Is that right? That is, I guess I don't know a detail in the GSI how they assimilate the UV, but I think that as long as you assimilate director means you give the speed and the direction, and probably have the same and the same effect of that. I don't know. Yeah. Thank you.
Okay. Any more questions from audience? Okay, I have one. Maybe the last one.
Okay.
You said good. Actually, that's 80% is your category for or threshold for good. Varies AMV wind.
Yeah.
How do you decide that 80% is good or not 75?
Yeah, this is very subjective. Yeah, very subjective. Because I did a new CAPS data, the sounding profile data assimilation before for Alaska model, and in that case I used the 80%. Get some suggestion from other people, from other person. Yeah, so that is I use that. But
okay, go ahead.
yeah, but your question is very interesting and very important. Actually, after this, I go back to my university. I still want to check. We'll change the quality to see if there is some change. I want to do that.
Yeah, because one question is how do they decide this percentage? Like what 80% even means in the quality, right? Or 50%.
Yeah.
Another is actually maybe we want to check the HRRRAK forecast over that area. That doesn't mean that actually your observation has to be 100% right to help the forecast. You have to provide useful information to you to correct your forecast. If HRRRAK has a big forecast error in that area, even your data is not like you 50% accurate, even 30% accurate. As long as it's actually correct, the analysis of forecast to right direction, it's still help.
Okay. Great.
So it's really not, when we do data simulation, we are not looking for perfect data. We're looking for useful data. Yeah. So it's interesting to see one is how they make this 80%, 70, and one is actually compare with your model if you can give right correction.
yeah, it's very true. And I also think because in the GSI, they still have a quality control there. So I think maybe we can try to degrade the quality of the data put into there. Say, if it's very bad, maybe you cut out by the GSI algorithm there.
Could be. There's a growth check there. It's another issue. Growth check is very gross. It's basically 7 times your observation error. Okay. 7 times. So if you're using low or if your observation error is small, your growth check will be very strict. But if your observation error is big, you will basically allow big innovation data get into your system, but because your observation area is large, this data will not impact your results that much. Okay. So there's this tuning process, but it's all, we need to check that.
Okay, great.
Okay.
Okay.
Any questions? Okay, great. Thank you.
Okay, thank you.